Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So in this video, let's have an German engineer Otto Mohr's approach in determining the moment of inertia with respect to any axis associated with a fixed point and the principal moments of inertia which will be located by the principal directions. So the idea is the given area is known and we can compute moment of inertia with respect to axis through a fixed point, let's say O, or through the centroid, and then the product of inertia also. Then we plot the values Ix and the product of inertia, and the other point is Iy and the negative of the product of inertia. They are represented by X and Y points. Then the X-axis and the Y-axis on the Mohr circle will be separated 180 degrees apart, or in this case double the actual angular spacing of the two axes, and they are the ends of the diameter of the Mohr circle. From the ends of the diameter of the Mohr circle, we can locate the center. The product of inertia at the center would be 0, and the coordinates of the center would be the average of Ix and Iy. Then from there, we use the geometric figure in order to analyze the moment of inertia with respect to the u and the v-axis, as well as the principal moments of inertia and the principal directions. So in this figure here, we have here the OA and OB axis, which may be the principal axis for obtaining the maximum and the minimum moments of inertia. And we also have axis through O, the U and the V axis, where maybe the question would be to determine the moments of inertia with respect to those axes. So this is the plot of the Mohr circle, or the shape of the Mohr circle. So after plotting Ix and product of inertia y, this point here, and that is associated with point x, or the x-axis, and the other coordinates should be Iy and the negative of the product of inertia. If the product of inertia is negative, then the other point pair for Iy would be the negative of the negative product of inertia, so it becomes positive also. So this is the x-axis, the first point plotted, and this is the y-axis, the second point plotted. Note that it is the diameter of the Mohr circle, and the rotation is the same, but double this time in the Mohr circle. So to locate the u-axis, for example, this is the u-axis. From the x-axis, which is this, we rotate double this angle theta here to locate the u-axis. And the u and the v-axis, which are originally 90 degrees apart here, will be 180 degrees apart in the Mohr circle. So this is now the v-axis. So the this point is the value of I sub u, the product of inertia with respect to the u-axis. And this value here, the v-axis at the end point of that diameter also, is the value of the moment of inertia with respect to the v-axis. Correspondingly, this distance from the center vertically would be the product of inertia with respect to the uv axis, and this is the negative of the product of inertia with respect to the uv axis. So if the axis OA is clockwise from the x-axis with angle theta sub m, Then in the Mohr circle, this is from the x-axis. We also rotate clockwise, and it is now this horizontal diameter where the principal axis can be found. So 2 times theta m. This is for the maximum moment of inertia. So you have here I max, and the minimum would be the opposite end, I minimum. So obviously, you can see that the maximum is the extreme right point on the circle, and the minimum is the extreme left point on the circle. And the circle should not cross the uh, negative region, or it should not cross to the left of this axis for product of inertia, because moment of inertia is always positive. It's only the product of inertia that can be negative. So I hope that uh, you can prepare the Mohr circle so that you can determine the moment of inertia with respect to the u and the v-axis, as well as the product of inertia. And we can locate the principal axis and then the maximum and the minimum moments of inertia. So this technique and procedure will be highlighted, or will be our procedure in the next problem or series of problems. Level 152. Use Mohr circle to determine the minimum value of Ix prime and the corresponding value of theta. So here is the given figure. So for our solution, let's divide the area into two rectangles in this manner, vertically, as shown. So we have rectangles 100 by 100 base and 200 height, and the other rectangle is 200 base, 200 mm, 100 mm the height. So for Ix, it is equal to 100 times 200 cube over 3 plus 200 times 100 cube over 3, because that's moment of inertia with respect to the base. So plus 200 times 100 cube over 3. So therefore, Ix is equal to 333.33 times 10 to the 6 mm to the fourth. Then for Iy, we have 100 cube times 200 over 3. Then we have to transfer the other one, which is 200 cube times 100 over 12 plus area, which is 200 times 100. Barred x is 200 and barred y is 50. So that's why we have moment of inertia with respect to the centroidal y-axis 200 cube 100 over 12 plus area 200 by 100, then barred x square, which is 200 square. So Iy is equal to 933.33 times 10 to the 6 mm to the fourth. Then for the product of inertia, for the first rectangle with respect to the centroid 0 plus area, which is 100 times 200, barred x is 50 and barred y is 200. Then plus the other rectangle uh, with respect to the centroid 0 plus area, which is 200 times 100, barred x 200, barred y 50. So computing product of inertia with respect to xy axis is equal to 300 times 10 to the 6 mm to the fourth. We then plot Ix comma Iy, so we'll just remove 10 to the 6, then we'll just put 10 to the 6 back later for the final answer. So we plot 333.33 comma positive 300 and 933.33 for Iy comma negative of 300. So let's prepare the axis. So this is the principal axis, the I-axis, and the product of inertia for the vertical axis. So imagine that each graduation is 100. So that 333.33 would be somewhere here between 3 and 300 would be 3 graduation up as shown. So this is the point X, and the other value would be 933.33 comma negative 300, and it is point Y, the other end of the diameter of the circle. We then connect the 2 points with straight line, which is the diameter of the Mohr circle, and let's draw the circle. So the circle is there, and then we locate the center. The center is simply the average of Ix and Iy, so average of 333.33 and 933.33. So 1/2 of quantity 333.33 plus 933.33, and that is equal to, so that's the X and that's the Y axis. Then the center C is again 1/2 of 333.33 plus 933.33, and that is equal to 633.33. We then consider this triangle, the right triangle. The base is equal to 633.33 minus 333.33, and that is equal to 300. So this is the leftmost point, therefore that's the minimum value of Ix prime, this one. So let's denote that by I minimum. And from the x-axis to the principal axis, which is here, we rotate counterclockwise. So this angle here is supposedly 2 theta, and the horizontal base is 633.33 minus 333.33, and that is 300 also. So obviously, if the opposite and the adjacent sides are equal, the value of 2 theta would be 45 degrees. And of course, from this point X to the center of the circle, that's the radius of the circle, and it is equal to the square root of 300 square plus 300 square. So that's also the x prime axis. So r is equal to square root of 300 square plus 300 square. So therefore r is 300 times square root of 2. Of course, that's times 10 to the 6. Don't forget that. Then I minimum can now be computed. It is equal to the coordinate at the center, which is 633.33. Going to the left to this point, that's the radius. So minus the radius. So Ix prime or I minimum is equal to 633.33 minus 300 square root of 2, or the radius. So from C to this point here along x prime axis, so I minimum can now be computed, which is Ix prime, and it is equal to 209.1 times 10 to the 6 mm to the fourth. Then from the figure, 2 theta, because the rotation is counterclockwise towards the x prime axis, or the principal axis where I minimum can be found, that's the positive rotation. So 2 theta is equal to 45 degrees, or tangent to theta is opposite 300 over 300. So 2 theta is 45 degrees. So that means theta is 22.5 degrees. So that's it for this problem, and I hope that you were able to follow and understand the explanation and solution. Level 153, use Mohr circle to determine the minimum value of ix prime and the corresponding value of data. So here is the given figure. So for ix, it is ix of the rectangle minus ix of the triangle. So 80 times 120 cube over 3 minus 80 times 60 cube over 12 for the rectangle for the triangle with respect to the base. So for our solution, we have ix equals 80 times 120 cube over 3, then minus 80 for the triangle times 60 cube over 12. So computing for ix, it is equal to 44.64 times 10 to the 6 mm to the 4th. Iy on the other hand is equal to 80 cube times 120 over 3. Then for the triangle, minus 80 cube times 60 over 4. So remember that. Or 1/4 80 cube times 60. So Iy is equal to 12.80 times 10 to the 6 mm to the 4th. Then the product of inertia of rectangle with respect to the centroid, 0, plus area 80 by 120, barred x 40, barred y 60. So product of inertia with respect to xy axis is 0, plus area 80 by 120, barred x is 40, barred y is 60. Then for the triangle with respect to the centroid, base square h square over 8. That's the direct way. B square 8 square over 8, or minus 80 square 60 square over 8. So minus 80 square times 60 square over 8. So product of inertia is equal to, for that orientation of the triangle, 20.16 times 10 to the 6 mm to the 4th. We then plot Ix comma product of inertia. So we just remove 10 to the 6 and put it back later for our final answer. So plot 44.64 comma 20.16, and the other partner would be 12.8 and negative to 20.16. So let's have the principal and the product of inertia axis. So imagine that each graduation is 5, so that 44.64 would be there, and 20.16. So that's the approximate location. This is the first point plotted, so therefore that's the x-axis, and the second point would be 12.8 comma negative 20.16, and that's the other end of the diameter, which is the y-axis from the figure. Then we connect the two with a straight line, which is the diameter of the circle. Then draw the circle as shown. So that's the x, and this is the other end, which is the y-axis and the circle. And the center would be the average of 44.64 and 12.8 here. So that the center is at 28.72 times 10 to the 6. So for this right triangle here from C to the right, that's 44.64 minus the center, which is 28.72, and therefore this is equal to 15.92. Then from the x-axis to the x prime axis, which is here, so that we can look we can compute minimum value of Ix prime. We'll call that 2 theta. And before that, we compute the angle here, and we will call that alpha. That's that one. So let's call this alpha, and this is 2 theta, which is counterclockwise from the x-axis to the x prime axis. Call that 2 theta. And 2 theta is equal to 180 degrees minus alpha. And alpha is arctan of 20.16 over 15.92. And of course, we need to compute the radius, which is square root of 15.92 square plus 20.16 square. So call that alpha. And this is the x prime axis. And the minimum moment of inertia is also found there. And let's indicate that I minimum. So again, let's solve for r and alpha first. So r is square root of 15.92 square plus 20.16 square. So r is equal to 25.69 times 10 to the 6 mm to the fourth. Then the minimum moment of inertia would be 28.72 minus the radius. So this 28.72 here minus the radius, which is this, to get I minimum. So I minimum or Ix prime is equal to 28.72 minus R, which is 25.69. Then let's put the times 10 to the 6. So I minimum is equal to 3.030 times 10 to the 6 mm to the fourth. Then tangent alpha is 20.16 over 15.92. So alpha is equal to 51.702 degrees. Then from the figure, 2 theta is equal to 180 degrees minus alpha minus 51.702 degrees. Then we can now compute theta, and theta is equal to 64.15 degrees. It is positive because it is counterclockwise from the x-axis. So that's it for this problem.